Now coming to the optical, optical isomerism. So for the optical isomerism, you must be knowing that there should be a chiral atom must be there. Then only it will show optical isomerism, which will be differentiated into dextro and levo compounds, so to say. Dextro means if the plane of polarized light is rotated towards the right, and if the plane of polarized light rotates towards the left, then it's said a compound is said to be as a levo compound. So, and what you find is that there should not be any element of symmetry. If there is an element of symmetry, then the overlapping is going to take place, and hence it will never be optically active in nature. It will be optically inactive in nature. Fine. So in this way we can have that is just like geometrical isomerism, we can have 4 coordination or 6 coordination spheres. But here something I have to say about it, that 4 coordination spheres, what you can say, compounds having 4 coordination spheres, that is the coordination number is 4, so to say. So it does not show optical isomerism. It does not show optical isomerism. The compounds having coming under 4 coordination sphere, it does not show optical isomerism. That is, in square planar complexes, all the 4 ligands and the central metal atom lie in the same plane. Got it? It lies in the same plane. When it lies in the same plane, they have got an element of symmetry. Got it? When they lie in the same plane, that means they possess a plane or axis of symmetry. As I said, they have an element of symmetry. Just now I said you, for a compound to be optically active, there should not be an element of symmetry. There should not be element of symmetries. One of the elements of symmetries are axis of symmetry, plane of symmetry, center of symmetry. This should not there. This should not be there in the compound. But in 4 coordination spheres in which it shows your what you can say, square planar complex, it has got that is an element of symmetry, an axis of symmetry, due to which it cannot be differentiated into dextro and levo, due to which it does not it is not chiral in nature, we can say that. Clear? That means it is optically inactive in nature, so to say, and hence it does not show optical isomerism, so to say. Got it? Now, okay, fine. This is about your square planar complex. What about tetrahedral complex? Fine. Now, in case of tetrahedral complex, it has it is not being possible to resolve into its components. It is not possible to resolve into its components. Components means into dextro and levo form. It is not being possible. Why? Due to the labile nature of the compound. The compound is labile in nature. We can say that. Labile means less stable. We can say. Due to the labile nature of the compound, which is less stable, in tetrahedral complex, the compound is less stable. Due to its labile nature, again and again I am saying, it is not possible to resolve into dextro and levo, that is into its components, so to say. So even if it has got asymmetric what you can say, tetrahedral carbon atoms, even if it is having or any other atom, we can say that metal atom it's having, so it must be optically active. But due to this particular reason, as it is labile in nature, it cannot be resolved into its components. So tetrahedral complex also does not show what you can say, optical isomerism. So that means 4 coordination spheres, square planar complex and tetrahedral complex, does not show optical isomerism. Remember these points which I said, because it may come in your reasoning questions. That why square planar complex does not show optical isomerism, why tetrahedral complex does not show optical isomerism. This is the answer which I said you. Now coming to 6 coordination spheres. Got it? 6 coordination spheres. Will it show optical isomerism or not? Yes, it will show. But here also, that is what you find is that Ma2B2C2. Got it? Ma2B2C2. Ma2BCDE. Then what you can say is that ABCDEF. Now all these are monodentate ligands or unidentate ligands. A, B, C, D, E, F, all these are monodentate or unidentate ligands. So let me tell you that these particular one, it does not show optical isomerism. This also does not show optical isomerism. This complexes also does not show optical isomerism. Why? Because the reason is the same. It cannot be resolved into its components, into dextro and levo form. It cannot be resolved. So here what we find is that if at all we will be able to differentiate into levo and dextro form, the what you can say, the resolution, that is the differentiation in dextro and levo, will be hardly 1 or 2%, we can say that. That means the complex which you will be getting it on resolution into dextro and levo, on resolving into dextro and levo. So hardly 1 or 2%, the yield will be very, very poor. Alright, so till now we do not have any adequate experimental technique to resolve these into complexes, alright, into the optical complexes, so to say. So till now, till today, we can say that they are also considered to be optically inactive in nature. They are also considered to be optically inactive. Theoretically, octahedral complexes containing monodentate ligands are optically active. Theoretically, these are theoretically optically active, but practically is not optically active. The reason I said it that the yield is very, very low. So we do not have an experimental technique to resolve them into its components. If at all we are able to resolve it, it is very, very poor. The yield is hardly 1 or 2%. We can say that. So what is the use of doing that? Now, then which particular one will show optical isomerism? Alright, which will show? That is octahedral complexes containing one or more, that is bidentate ligands, so to say. Alright, bidentate chelating ligands. That also, let me add the word bidentate chelating ligands. You know what are chelates? Chelates means along with the central atom it forms that is nothing but what I should say, that is a ring complex is being formed. That is called as a chelating ligands. So it can be that is 5-member chelate, or it can be 6-member chelate. We have already discussed. So in this way, it forms a chelating ligands, bidentate chelating ligands, so to say. Only undergoes optical isomerism. It forms optical isomers. Bidentate. Got it? Denticity is 2. We can say that. Means it has got 2 donor atoms. So now the coming under it, what we can say, that is MAA, that is whole thrice, we can say that N plus minus, MAA whole thrice N plus minus. It can be any charge. AA is your bidentate ligand, we can say that, similar ligands. Now we can give the example is here, that is we can say here, see here, we can say is, we can say we can take here OX, oxalate. This is your OX, oxalate. Clear? So here CR, OX is oxalate. So CR, we can say oxalate is minus 2, minus 2, minus 2. Each is minus 2, so minus 6, and CR is plus 3. So it will be minus 3. Now here what we find is that this is coming under this particular one. It comes under, that is what is that? Dextro form, we can say that, because on the right hand side the more number of ligands is there, so it is dextro. Alright, we can understand theoretically in this way. But if it is being changed, we can say that if it is being changed means, suppose here we are having, that is OX, on the left side and the right side only 1, same thing, and instead of N plus minus we are having, that is 3 minus or minus 3, whatever it is, we can say that. So then we can say this one as LEVO compounds, we can say that. This is dextro and this is LEVO compounds, we can say that. Clear? So we can take any other, like instead of that is OX, we can take EN also, ethylene diamine. Here EN, here EN, here EN. EN, EN, we can say that also can be taken. It is also coming under bidentate ligand, so to say. So next is another one is, we can say is nothing but MAA whole twice. One A will remove, and instead of that we will bring a monodentate ligand, that is AB, we can say that. Clear? So what we can have it? Alright, what we can have it for that? I said you, it is MAA whole twice N plus minus. Clear? So here we can take same thing, cobalt or chromium or something, same thing we are taking. Let us say we are taking cobalt only. Alright? Clear? Now dextro means, definitely in case of dextro, this right side, that is the number of ligands, or the molecular weight of the ligand will be more, we can say, in case of dextro. So in case of here, what we will see is that here we will be taking, that is EN. Alright, here will be one EN, MAA whole twice, sorry, I forgot to write AB. that is AB, MAA whole twice AB. So we got here En, and AB means monodentate ligand. So here let us say we are putting ammonia, and here we are putting Cl. Alright, now En is a neutral ligand, ammonia is a neutral ligand, we can say that, and Cl is -1. So CO is +3 -1, so it will be what? +2. So this is your dextro. Now levo, what it can be? Same thing it is. Just little bit we apply the common sense here. So what it's En, this side is there, so En will come this side of course. Alright, now here this is the En is there, now the En shifts the other side. Got it? So we can say here the En shifts. This is your En, and the ammonia and the Cl remains the same. Here the ammonia, and here it is Cl. That is nothing but +2. So this is your dextro and this is your levo. We can say that. Now if you say, if you want an meso form, meso means which contains 50% dextro and 50% levo. It is optically inactive in nature, but 50% dextro and 50% levo, we can say that. It is being present. Internal compensation. Internal compensation means the internal arrangement of the compound is such that it contains 50% dextro compound and 50% levo compound. That means this is 50%, this is 50%, is present internally. I am not mixing it up. If I am mixing it, that is said to be as a racemic mixture. That is due to external compensation. But if internal arrangement is such that, then if it is 50% dextro and 50% levo is present in a given compound, so it will be optically inactive. Why? Because 50% dextro means 50% is rotating towards right. 50% levo means 50% is rotating towards left. Got it? Net rotation is what? 0. We can say that. Clear? So hence it is optically inactive in nature. So what should be the diagram in that case? A small one I am drawing it because I don't have the space here. And the small one I am drawing it. This one only. That is CO. You can see it here. Clear? So here we will put one En, and here we will put one En. Here it is NH3, and here it is Cl. We can say that. This is your meso compound. We can say that. This is your meso compound. Of course, +2 is there. This is your meso compound. Clear? So it is said to be meso compound. This is optically inactive in nature. So that is MAA whole twice. That is AB. We can say that. So in this way, we can have optically active compounds. We can say. So here also MA whole twice AB. We can take it MAA whole twice A2 also. I can take it. Alright, I can take this also. That is MA whole twice A2, N plus minus. In A2 what we can do? This is NH3, this also will be NH3. Suppose if I will say no, this is Cl, then this also will be Cl. Means the monodentate ligands will be the same. A2 means monodentate ligands is same. AB means monodentate ligands are different. Here the monodentate ligands will be same. That also we can give an example. Clear? So here it is Cl, it is a Cl. So here it is Cl, Cl is -2. So it will be what? +3 -2 is +1. So here also it will be +1. Here instead of ammonia, I will take it as what? Cl. And here also same thing, I will take it as Cl. So +1, and here also it is +1. So hence it comes as dextro, levo, and this is your meso compound. We can set it. Clear? So these are the different types of optically active compounds. So this comes under optical isomerism, so to say. Okay. Thank you.